The work in this video is a joint effort between Professor Philip Bekaert, Tim Vervoort, Bram van Herle and Nick Michiels in the context of the OmniDrone project. The camera system we have been developing in the OmniDrone project is a portable system with 4 cameras with each a resolution of approximately 4000 by 2000 pixels. Mounting them with wide-angle fisheye lenses allow us to achieve double overlap between views. Each camera can capture a 220-degree field of view. Because of the nature of the fisheye lenses, the captured frames are highly distorted. A more practical representation is to transform the raw fisheye views into an equirectangular 360-degree format. To achieve this, we first need to extract the proper distortion parameters by analyzing calibration patterns in front of the individual cameras. If needed, the 4 equirectangular images can be stitched together into one single omnidirectional frame. However, we have seen that most of the proposed algorithms in this project don't rely on such composited frames, but can work directly on the individual cameras. Although the prototype of the camera is portable, it is not yet sufficiently stable and solid to be mounted under a drone. However, we have been using it to evaluate different algorithms in the project. Here, for example, we use the camera system to capture an indoors and outdoor sequence at ESAT, with complex camera motions to validate the SLAM algorithms developed by physics. The camera is mounted on a tripod and a trolley, while the recording is done with a laptop. Each sequence consists of 4 different camera tracks. An interesting line of research of EDM is automatic broadcasting. Because of the high-resolution multi-camera systems we have been developing, we are able to capture the entire scene of interest all at once. The camera framing itself can be postponed to the post-processing stage by simulating virtual camera tracks. This is only possible because the high starting resolution. For example, in 4K footage we can simulate up until a 4 times digital zoom and still retain 720 pixels output resolution. The idea of this project is to make this manual virtual framing and editing as automated as possible. So if we do a quick recap and look back to what we had last time, we first started with the automatic broadcast of a single person in a multi-view camera setup. The person is tracked in each frame and the proper virtual camera framing is defined. A couple of additional automatic rules are used to decide when to switch between camera views. Then we extended this approach towards multi-person broadcast. This can be seen as an equivalent to traffic and surveillance footage. Here the key challenge is to achieve proper tracking of multiple individuals over time. A user can then decide on one or more persons to follow and cut out. This works pretty well when applied to the individual cameras alone. However, if we want to cut from the person in one view towards the same person in a different view, we also need person re-identification. Otherwise, it is simply impossible to link similar persons across the different viewpoints. Last time I presented some of the initial results of our person re-ID. We continued working on this and applied it to the full sequence. The goal is that for each bounding box in one view, we iterate over all bounding boxes in another view and identify the best matching person. The metric to decide if one person matches the other one is based on the Euclidean distance between the features of both bounding boxes. We experimented with 2 different types of features, one built with a traditional image processing approach, the other one relies on deep person re-identification. Because we work on video and have all persons tracked over multiple frames, we can utilize features from previous frames to build a more robust mean feature over time. Once the best match is identified, we assign the same person ID to that bounding box. In this case it works pretty well because both cameras are quite close together and the changes in background is relatively small. But it's likely to be much more challenging when the viewpoints are further apart from each other. To test our person re-identification on a more challenging dataset, we evaluated it on the online 360-degree free viewpoint dataset of Thomas Mocky and colleagues. The dataset consists of 40 omnidirectional cameras, evenly spaced in an indoor environment where multiple persons are walking around freely. We first transform all cameras into the equirectangular format and execute the LightNet YOLO detector of IVIS together with our person tracking algorithms. Then we generate re-ID features for each tracked person in each camera and try to identify similar persons across views. To decide on when to cut to a different view, we introduce the same directing rules of the person tracking. For example, the view with the larger bounding box or a view where the bounding box of the tracked person is increasing. To show you a result, in this example we selected the man with the white sweater and tried to follow him across the room. The results are quite promising. Overall, the person continues to be in frame. However, it is far from perfect. Occasionally, the system switches to a wrong person because the re-ID features are not always unique. The rules for viewpoint selection are relatively simple and can be extended in the future with more realistic rules. For example, right now, it does not make a distinction between front-facing and back-facing angles. Another important remark is that the approach is still rather slow, because the processing time increases quadratic with the number of persons and viewpoints. As a result, the technique is limited to work offline as a post-processing step. However, we believe that it should be feasible to make it real-time in the future. Apart from the challenges in Re-ID, we also try to increase the capabilities of the framing and directing tools for more complex scenarios. For example, here we have an in-house recording of a basket game with 3 wide-angle cameras, 2 basket views and 1 side view. Instead of just single-person tracking, we now have included rules for group tracking. The detection of the individual persons is shown in red. The camera framing is shown in yellow. Our approach is that the user of the system can define a set of high-level selection parameters per viewpoint. These parameters will be chosen in function of the use case or application domain at hand. For example, for the basket views, a growing bounding box is most important because it suggests that the players are moving towards that basket. On the other hand, for the side view, a fast-moving bounding box is most important because there it suggests that the players are moving away from one basket and are running to the other side of the court. The result is a broadcast where both framing and viewpoint selection are executed automatically. However, the user is still able to give manual input on how the system behaves. Most of the algorithms we have developed up until now are proof of concepts and are running offline. On the other hand, we have the Studio.One recording and production system that is able to process in real time multiple ultra-high resolution wide-angle camera streams at low operational cost. The system is capable of running a large number of virtual camera cutouts in parallel. And, in this system, the virtual framing is done manually with only one operator. The system has proven its worth for different application domains, from entertainment towards conferences and sport events. As I just mentioned, the Studio.One system is able to substitute manual framing with digital framing, but still it requires manual labor to set up each individual virtual framing track. This needs to be done on each camera viewpoint and is rather time consuming. Our next goal is to integrate the automatic broadcast algorithms with the online processing capabilities of the Studio.One system. Instead of using a joystick to manually set up the virtual framing, we can use person tracking to automatically generate possible attractive camera tracks. This would be already a huge improvement, since then the operator can mainly focus on the creative part by selecting the right output views. Additionally, we can also use the viewpoint selection criteria to make suggestions about what viewpoint could be interesting to broadcast. The basket game I showed earlier is processed in an offline fashion and then edited into the final result. The first step of integration was to export the editing rules into a format that is understandable by the Studio.One software. The result of the integration is shown here in a side-by-side view. There are some main advantages. The playback can now be done in real time, but most importantly, the virtual cutouts are now physically correct because the proper camera transformations can be applied in real time. For example, the initial result on the left has incorrect camera distortions, but are now taken into account in the improved result on the right. The next step in this OmniDrone project is the full integration of our detections and tracking algorithms for multiple persons with the live system. We have some initial results on the integration of the tracking of a single person in a live multi-view setup. For this, we integrated the YOLO detector, which can be applied directly to the recorded frames. The most challenging next step is to integrate the more complex multi-person tracking and camera selection tools. Once the multi-view tracking is up and running in real time, adding additional rules should be rather straightforward.